This is part 2 of lecture 10, Digital Pulse Modulation 107. This is the second to the last video lecture that I will upload, and we will just continue our discussion here on digital pulse modulation, specifically in saving the bandwidth or maybe reducing the complexity of your system. So there are two approaches there. Just a review on the last lecture. I introduced to you the quantization techniques. How do we quantize signals that have large crest factors, non-uniform quantization. There's also uniform quantization. How do we represent the quantized signal into bits, and the use of pulse code modulation in your time division multiplexing scheme. Okay. But there are practical issues, as with all of our communication schemes, right? There are practical issues on using pulse code modulation. The benefits of pulse code modulation is the robustness against noise or interference, and it can be used with PDM. However, as we've seen in the previous lecture, if you want to transmit a PCM signal, you have to use high bandwidth, okay, that is directly proportional to the number of bits that you will use. And this imposes an increase in transmission bandwidth, right, due to the shorter duration of pulses, an increase in system complexity. So even if it's robust against noise, you want to add that robustness, those advantages, your system becomes more complex. And this is kind of a general trade-off when we're designing communication systems. You want a better communication system, everything becomes more complicated, everything becomes more complex. So if we want to reduce the complexity, or if we want to increase the bandwidth efficiency, there are two approaches. Right? We can increase the complexity, but we reduce the bandwidth using what we call the differential PCM. Or we increase the bandwidth for a simpler system implementation, and this is your delta modulation. So how do they work? A differential PCM, because it uses the concept of autocorrelation. If we try to sample a signal, right, the similarities in a signal with itself, we can use those similarities with itself to predict the next value of your transmitted signal. Right? So for voice signals, your smaller time difference means higher correlation, and that is true with all signals. Okay, so if you have a signal that is very slow, or its autocorrelation function is very large, right here. Okay, so the signal changes its statistical properties in a slow manner. We can use differential PCM to be able to represent the signal with less bandwidth. So if we sample the signal at different points, right, and we know that the current value is correlated to the past values, depending on how fast the statistical properties of the signal change with time. If it's highly correlated, then we're able to predict this based on the data that we get from the past sampled values. So instead of just transmitting the immediate values, since they are correlated, why don't we just transmit the difference between the values? Okay. So we sample the message at a rate higher than the Nyquist rate. This ensures that the autocorrelation of the signal will be very this autocorrelation function here will be very wide. Okay. And with that, we can make a good guess of the current sample using the value of the past samples. So if we use these samples here, we can predict what will be next. Right? So if we take in more signals, more of the past, if you have more past knowledge of the signals, we're able to predict what will be the next value of that signal. Okay? So for a given analog signal, we use the Taylor series for this. Using the Taylor series, we can predict or estimate the future value as shown right here, So take a small time difference delta t. Using the Taylor series, you get these weighted sum of your signal, okay, based on delta t. If delta t is very small, then we can approximate it as this. And since we're sampling the signal, we will be discretizing this in time, which will result into a difference equation. And with this, we can predict m of k plus 1, which is m hat of k. Okay? And that is equal to this equation right here. And in this case, we're getting two samples from the past to predict the future value. Okay? So if we just get the difference, if we only know the difference between the two samples, we're still able to estimate the current output. Right? So if we use more samples, the expression will become more accurate and we add more terms. But so in general, it looks like this. And you can implement that using a delay line with some weights, and you add them all up. So you get your output. But your system becomes more complex. Right? So how does that work? So you have your sampled message here, okay, and then you have the estimate of the message here. You get an error, and you put that in a quantizer, which will be quantized and then encoded. Then that quantized value will be fed back to the linear predictor. Okay, and with that, you're able to get a DPCM symbol right here. And this is already the difference between the sampled values. Okay. The receiver diagram looks like this. The DPCM symbol will be decoded. Okay. And linear predictor, this signal will be fed back to a linear predictor. And then you get an estimate of the current sample, and then you plug that in through an LPF, you'll recover your original message. Okay. So if we filter this out, you'll get your original message. This is an estimate of the series of samples as if it was a PCM signal. So an estimate of your PCM signal. And of course, if you want to be more accurate, your linear predictor must be more complex. Okay. Now the other one, for delta modulation, the signal is oversampled to purposely increase the correlation between the adjacent sample. And then what the delta modulator does is that it will output bit 1 or bit 0 depending on the two samples, depending on their difference. Okay? So it works like this. The transmitter block diagram looks like this. You have a sampled message here, then you reduce that message, the sampled message, from the previous symbol that you get. Okay? And then you have a difference. In this difference, if it's negative, then this 1-bit quantizer will output 0. If it's positive, the 1-bit quantizer will output 1. And this signal will be encoded, and you have your DM sequence right here. Right? Now you're given a sequence of bits. It's just 1 bit per symbol. Right? But when you try to recover that, you will the sequence will be decoded. You have the difference between the two samples, not the difference between two samples. Then if you add that to the previous value, you get your current value. And if you put that through a low-pass filter, then you will be able to recover the original signal. Okay? And how it works, it looks like this. If the current bit is less than the current value of the signal, your DM signal will rise up. Okay, if at the current point the signal is still greater than the the signal is still greater the signal is still greater than the current value, it will rise up, and it will continue to do so until when the signal sampled here, the DM signal already greater than the message signal. It will go down. The issue with this is that there could be large errors due to a fast changing signal, right? Or some form of cycling error because of a slow changing signal. And that's granular noise. And the other one is slope overload distortion. And the slope overload distortion occurs when delta is too small. Your converter cannot keep up with the signal because it's too fast. Granular noise happens when delta is too large, right? And the staircase approximation just oscillates because of that. That's your granular noise. If you try to pass that through if you try to pass that through an LPF, you have a sinusoid function at the output. Okay? To summarize the difference of the three, if you want smaller bandwidth, you need to increase your system complexity, and that's achieved with DPCM. It's very complicated, but at least you save bandwidth. But if you want the system to be simpler, you have to sacrifice the bandwidth. And this is a fundamental trade-off. If you want to have a larger bandwidth, if you want to be more bandwidth efficient rather, you need to increase the system complexity. And this will also be true as you study more advanced communication systems. It's still apparent that if you want to be more bandwidth efficient, you have to increase the system complexity. Okay? And that's the end of this lecture. If you have any questions or have any comments, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.